In the last lecture, we defined sample spaces, outcomes, and events, and started reasoning about how to calculate the probability of different events. In this lecture, we'll expand on those ideas by thinking about how knowledge of one event influences the probability of another event. To introduce some of the concepts, let's think about a sample space that models rolling two dice. Here, the roll of the first die determines the row, and the roll of the second die determines the column. And in the corresponding cell, we have the total on the two dice. And given this representation of the sample space, we can define various events as regions within this grid. For example, if A is the event that one of the dice rolled at least a 5, then we can highlight the region of the sample space corresponding to event A. If the first die rolled at least a 5, then we would be in the bottom two rows, or if the second die rolled at least a 5, would be in the right two columns. And so having highlighted the portion of the sample space corresponding to one of the dice rolling at least a 5, we can think of the probability of this event as corresponding to the fraction of the total area that's within this region. And if the event B is that the total on the roll was 10, we can similarly highlight that region. And similarly, the probability of B is the ratio of the areas, so 3 out of 36 or a 12th. When we talk about conditional probabilities, we are conditioning on knowing that some event has occurred. If we write probability of B given A with a vertical bar, what we mean is that we know that event A has happened, and so given that knowledge, how do we update the probability of B? Well, returning to the areas, if we know that event A has happened, then we know that the possibilities are restricted to the red region, and so now there are only 20 possibilities, and so B occurs in 3 of those 20 possibilities, and so the probability of B given A is 3 out of 20. We can extend our examples by defining some more events. The event C, that the total was at most 5, corresponds to the upper left region of our sample space. And the event D, that one of the dice rolled a 2, corresponds to the second row and column of our chart. With C and D, we have two events that are overlapping, but we no longer have that one event is a subset of the other. We can again describe their unconditional probabilities in terms of their area. The event C has an area of 10 out of the sample space that has 36 boxes. And D has an area of 11, so a probability of 11 over 36. We can think about the conditional probability of C given D. If we know that event D has occurred, we know that we are in the 11 boxes of the purple region. And of those 11, 5 are also within the green region. And so the probability of C given D is 5/11. Or we could think about that if we know C has happened, what's the probability of D? If C has happened, we're in the green region, and 5 of the boxes among the 10 are also in the purple region, so the probability of D given C is 5/10. We could also figure out conditional probabilities for other pairs among these four events. Some particularly interesting ones are the probability of A given B, or the probability of A given C. If we know that event B has happened, then we're in the blue region, and so we must also be in the red region, so this probability is 1. And if we know event C has happened, then we know we're in the green region, and the probability of event A happening when we're in the green region is 0. In a moment, we'll give a formal definition of conditional probability and base some other definitions and theorems on it. But first, I want to abstract this idea of our sample space as a region so that we can use Venn diagrams to think about conditional probabilities. If we generalize this idea of areas giving us probabilities to an arbitrary sample space, then we're thinking of the sample space as some region, and that sample space is made up of subregions that correspond to each of the possible outcomes. If the outcomes all have the same probability, then we can think of the region as a grid, but if the outcomes have different probabilities, then the area that corresponds to each outcome would be proportional to its probability. If some outcome is more likely, then it would have a larger area. Then, like we did here, for different events, we can illustrate the subregion of the sample space that encloses all of the outcomes in a given event. So abstractly, we could draw our events like C or D as regions in the sample space. And then the overlap between those two regions is the event C intersect D. We can also think about the complement of an event, that is the outcomes where an event didn't happen. So the complement of C would be everything that is not in the set C, and everything that is outside either of these two regions would be the complement of C union D. Where, as we saw in our activities, the complement of an event is all of the outcomes that are in the sample space but not in that event. And the reason to draw this sort of Venn diagram is I find it incredibly helpful in thinking about conditional probabilities. Specifically, if we're thinking about the conditional probability of C given D, given D means we know that we are in the D region. And so what's the probability of C given D? If we know event D happened, the probability that C also happened is the ratio of this intersection area to the total area of D. And that corresponds to how we were calculating the conditional probabilities in our dice roll example. So our formal definition of the conditional probability A given B is exactly what we just described. The probability of the intersection of the two events divided by the probability of the event that we are conditioning on. So in our Venn diagram, the conditional probability C given D is the probability of the intersection divided by the probability of D, and the conditional probability of D given C is also the probability of the intersection, but in this case divided by the probability of C. And that gives us a very nice relationship between the conditional probabilities of D given C and C given D, which we can formalize as a theorem. Bayes' rule gives us a conversion between the conditional probability A given B and the conditional probability B given A. If we know the probability of B given A, then we can multiply by the ratio of the two probabilities A and B to get the conditional probability A given B. The proof of this theorem requires only our conditional probability definition and some basic algebra, and corresponds exactly to the intuition that we just gave from the Venn diagram. We can start with the definition of our conditional probabilities A given B and B given A. And then in both cases, we can solve for the probability of the intersection. And now that we've solved for the probability of the intersection, we can substitute. And then when we solve for the probability of A given B, we get our formula. So if you're thinking about the Venn diagram, where the conditional probability is the ratio of the intersection to the event that we are conditioning on, or if you've just stepped through this algebra, Bayes' theorem may seem like a really obvious result. But if you ask me which is the most practically useful theorem from this entire class, my answer would probably be Bayes' rule. My justification for that claim is that whenever you're trying to reason formally about some model that describes an interaction in the real world, you are almost always going to have to reason about conditional probabilities. And if you are reasoning about conditional probabilities, then Bayes' rule gives you a way to translate the sort of evidence you might be able to gather into the sort of prediction you might want to make. There are tons of interesting examples out there of applications of Bayes' rule, and I'll post a link to a video about at least one such example. Before we move on, let's use Bayes' rule to verify our conditional probability calculations for C given D and D given C. Bayes' rule says that the probability of C given D should be equal to the probability of D given C times the ratio of C over D. So let's check our arithmetic. So we have C given D should be D given C times the probability of C over the probability of D. To make things cancel out nicely, let's express both of these as a probability out of 36. And we could also make things cancel more nicely by expressing the probability of D given C as 5/10. And now the 10s will cancel. And we're left with 5/11, which is the probability of C given D. if we consider events E, that the first die rolls a 3, and F, that the second die rolls a 5 or 6, and calculate conditional probabilities, here's what we get. The probability of E given F is 2 out of 12. And the probability of F given E is 2 out of 6, which is still 1/3. And so here we see that when we condition on F, that doesn't change the probability of E, and when we condition on E, that doesn't change the probability of F. And so here, if we know that event F has occurred, that doesn't give us any new information about how likely E was to have occurred. The probability given that knowledge is the same as the unconditional probability before we had that knowledge. And this should make sense if we think about what these events are modeling, where E depends only on the first die and F depends only on the second die. And so knowing what the first die rolled shouldn't give us any information about the totally independent roll of the second die. And so we call these two events independent. We define two events to be independent if the probability of both events happening is the product of the probability of each individual event happening. So here, the probability of the intersection is 2 out of 36. And that's equal to the product of the unconditional probabilities of events E and F. Of note, this equality does not hold for any pair of events. We are specifically saying that when this holds, we have independent events. And one of the most common mistakes in probability is multiplying probabilities of events that are not independent. If, for example, we had multiplied the probabilities of A and B earlier, we would have gotten a wrong answer for the probability of both A and B happening. This product only gives the correct answer for events that are independent. But we can equivalently define independence in several other ways. For example, here we motivated independence as the probability not changing when we conditioned on the other event. And so we could say that events A and B are independent if, when we condition on B, the probability of A doesn't change, or when we condition on A, the probability of B doesn't change. And we could prove that events are independent by this definition if and only if they are independent by this definition or the original one. We could have also defined independence in terms of the complement of an event. Here, the probability of E is the same whether we condition on F and get 2/12 or condition on the complement of F and get 4/24. And so we could have used that to give even more equivalent definitions of independence. And if two events are not independent, we can call them dependent. And so all pairs from A, B, C, and D before were dependent events. If we have events that we know are independent by any of the equivalent definitions, then we can take advantage of this product of probabilities rule to reason about combinations of events. Here's how I would approach figuring out the probability of rolling a 6 among 4 dice. Just like when we're doing combinatorial counting of lists, when we have an at least condition, it's typically easier to reason about the complement of that condition. And so if the event E is rolling at least 1 6, then the complement of that event is rolling no 6s among the 4 dice. And we can break this event down into events for each of the 4 dice that will be independent. So we can think about the event that we roll a 1 through 5 on the first die, and the second, and the third, and the fourth, and each of those will be independent events. So the probability of rolling a 1 through 5 on any of the dice will be 5/6, and so the probability of rolling 1 through 5 on the first die, and the second, and the third, and the fourth is the intersection of the events F1 through F4. And this intersection is the complement of our event rolling at least 1 6. And since these events F1 through F4 are all independent, we get 5/6 multiplied by itself 4 times. And that has a roughly 48% probability. And so, since the probability we were originally looking for was the complement of this intersection, we have 1 minus this as the probability of at least 1 6. And so if we roll 4 dice, we have about a 52% probability of rolling at least 1 6. So when we have events that are independent, we can figure out the probability of all of them happening, that is the intersection of those independent events, by multiplying all of their probabilities together. But if we have events that don't meet our equivalent definitions of independence, then we have to fall back on our union and intersection rules from last time to figure out the probability of those events overlapping.